Hello, this is chapter 12, section 1, the last chapter of our book. Yay! And we are going to learn about chi-square tests in this particular chapter for the section 1. And it's a specific type of chi-square test called a goodness of fit. And when do we use this type of test is when there is one variable, one categorical variable, as in the color of the candy. And then there are, multiple colors of candy, or so there's one category, but there's just variations of that one category. So this is categorical data. If you remember this from chapter 1, maybe not, maybe yes, but regardless, we're doing it. So why would we do a chi-square test instead of a proportion test here? One of the reasons why chi-square tests are really great is even if it's a proportion technically, this is 1, 2, 3, 4, 5, 6 proportions. No one wants to do a 6 proportion hypothesis test. Absolutely no one. I mean, I love math, but efficiency is more important than especially in the real world. When you're in industry, when you're working for a firm, they're not going to wait for you to do 6 proportion tests. You want to do a chi-square test and call it good, for example, here. Okay, so in these particular questions, there's usually a claim being made, a claim of a distribution. And according to Mars, M&M's milk chocolate candy bars, let's see, where is this? Mars Inc. right there. And it's in Hackettstown, New Jersey. These are the distributions of brown, red, yellow, green, orange, and blue. But in a specific instance where we sample 60 candies from a bag, we might not get this exact proportion. And so from 60 candies, this is what actually happened. These are called observed counts. So you grab 60 candies, random sample somehow, and then from that you count how many of each color. And so when you state your hypotheses, in this case, it's going to be words. You're going to state that the null is that it is the same as the claimed distribution. So the distribution of the color in the large bag of M&M's milk chocolate candies is the same as the claimed distribution. And then the alternative is that it is not the same as. So and you're going to have to reword exactly the same stuff, just change it to is not the same. Do not take shortcuts. Do not say ditto like the previous one, and don't do this and go same. Don't do that kind of stuff, especially not on the AP exam. You can do it this way, but please don't. Because if you write at least one PI is incorrect here, you're going to get it wrong. So please be very careful. And then you still have to write where P is the color of the true proportion. I mean, look at this. Doesn't look much less than this. So might as well just use the words. Okay, it's a little easier. And then here it is why we don't do at least one. It has to be at least 2. You could read into that if you like. I'm going to move on. Comparing observed and expected counts. So here is the expected count. And what does that mean? There are 60 candies we pulled out of the bag as a sample, and the claim says 12.5% is brown. So if we pull out 60 candies and 12.5% is what we expect for the brown to be, there should be 7.5 brown. And remember, the halves, don't stress too much over it. It's kind of like averages. It's just a number, but we don't round here. Don't ever round expected counts. So you're just going to keep them as is. Imagine them being kind of like an average-ish. but the expected amount of brown is 7.5. The expected amount of red is also 7.5 because it's the same proportion from what the company claims. 12.5, 12.5, 12.5, 12.5, and then there's 25, 25. There's probably a marketing reason for that, but I don't know the reason. So then that means that the orange and blue, of course, is going to be 15, expected to be higher because the percentage was higher. So now we have two things here we're looking at, two sets of numbers. We have this set of numbers, which are the observed counts, and this set of numbers, which are the expected counts. And the chi-square test statistic is like, it looks like this. It's not, the way I do it is I just do one slanted line and then I do this and put a square. To calculate that, you need to take your observed, subtract your expected, square it, divide it by expected, and then add them all up, sum. So in short, you're doing this minus this, and then you're squaring that number, and then you're dividing it by 7.5, this. And then you do this minus this, square it, divide it by 7.5, this minus this, square it, divided by 7.5, etc. This minus this, square it, divided by 15. And then you add all of these numbers up, and that is your chi-square test statistic. Which we're not going to do because the calculator is going to do it for us. However, if you really must calculate one by hand, that is an option. Okay, what is a chi-square test statistic, and what exactly is a chi-square distribution? So a chi-square distribution is the third of the kinds that we've learned from the beginning of the year. At least for inference, we have normal, right? And we would use a z-star for that for all of our formulas, or a z-score. If it's a test statistic, this is the test statistic. Okay, and then this is for the confidence intervals for the critical value. We also did, t distributions where the tails are a little fatter here. And this is, your test statistic here was the t-score. We just called it t when we calculated it. And then for the confidence intervals, we would use t-star, right? Okay, well, this is the third type. The third type of distribution is called the chi-square distribution, and it looks more skewed, as you could see. It gets less and less skewed as your degrees of freedom increase. And if it's 1, it's like very steep little, probably like goes up that way. I'm not even sure why it's just cut off there. But it is a very skewed distribution when the degrees of freedom are pretty low, and it gets more and more leveled out a little bit as the degrees of freedom gets higher. And so the chi-square test statistic is basically equivalent to a t-score or a z-score. So in the chi-square, this is the test statistic. All right, so the conditions are similar. Not exactly the same for the large counts, but we'll talk about that in just a couple of seconds. But the random definitely is the same. 10% is the same. Large counts, notice it says large counts and not normal/large sample, because this is technically a proportion problem, but a multiple proportions problem. So that's why it has the conditions related to the proportions type of questions. Okay, but what's different is we have to check that the expected counts are at least 5. So that's definitely different. And yes, you need to list all your expected counts on your paper. And it says it here, not the observed counts. We're not checking for the observed counts. And make sure to write and label the expected counts on your paper, or you won't receive credit. This is super important. Okay, so the chi-square test statistic for goodness of fit, we talked about this already. What's different about also the degrees of freedom here is that degrees of freedom is number of categories minus 1. It says it with words here, a little shorter version. Degrees of freedom is number of categories minus 1, so 1 less category. In the M&M problem, since there was 6 categories, colors, it would be 6 minus 1, 5, degrees of freedom of 5.